Very good morning, my dear students. I hope everybody is doing well. We are going to start a new chapter in this session. The name of the chapter is Magnetism and Matter. Let's start. Magnetism and Matter. So, the last chapter was Moving Charges and Magnetism. That's called Magnetic Effects of Electric Current. Here, we are discussing completely about magnetism. So there's no electric current topic is involved here. Whereas in the last chapter we had discussed the relation between electric current and the magnetic field. Here completely about the magnetism we are going to discuss. Let's start. The first topic is, see, it's clearly visible, it is magnetism. What is this magnetism? The magnetism is the property of a magnet, right? Which attracts the magnetic substances. The magnetic substances. The magnetic substances will be like iron, nickel, steel, cobalt, etc. Here, what you should understand, this is the property of a magnet which attracts the magnetic substances and other magnets also. What is the magnet? From this point onwards, the chapter continues. What is the magnet here? Magnet, it is a substance which can attract these magnetic substances or another magnets. And you should know the basics about the magnet. There will be two types of magnets are available for us: natural magnets and artificial magnets. Natural magnets and artificial magnets. The natural magnets, you can see from the lower classes also you might have learned. You may got forgot. Don't worry about it. We'll start from the basics. Natural magnet. The first natural magnet was found in Greece. That was Fe3O4, oxides of iron, iron ore. Iron ore was the first magnetic substance which was naturally found in Greece. So this is also called as magnetite. What is that? Magnetite. Later, Chinese people were identified a substance called lodestone, that is also called as leading stone. Okay, so this is used for navigation purpose. Navigation purpose. So these two are called natural magnets. All the artificial magnets what we are going to learn now were made from these natural magnetic substances only. Clear? Now, artificial magnets. And depends on the requirement. For example, you see, there are some magnets which will be in a circular shape. 90% of the cases we assume a magnet means there is a bar magnet which will have two poles, north pole and south pole. And in some electrical devices, the magnets we use as horseshoe type magnets. Like the shape of the magnet will be U-shaped. In some cases, we use a dumbbell shaped magnets also in some electrical devices, right? Why we use a magnet? That's what our last chapter discussion, magnetic effects of electric current, right? Electric motor, electric generator, wherever there is a rotating effect is there, the magnets are must. Clear? Now, depends on the requirement, we make the artificial magnets of different shapes and sizes, right? So artificial magnets are like this. The first important artificial magnet we should know is a bar magnet, which will have two poles, north pole and south pole. About polarities in detail we'll be discussing later in this session itself, right? Let's concentrate on this one. This is called a bar magnet. And just now I have told you, so there is a U-shaped magnet also. So that U-shaped magnet is also called as horseshoe magnet. What is it called? Horseshoe magnet, right? So let me write here. So this is horseshoe magnet. Is it clear? So there will be some ring shaped magnets will be here, and there are some dumbbell shaped magnets also are available here. So like this dumbbell shaped magnets also are there. Depends on our requirement. And even you might have seen a compass needle or a magnetic needle that also comes from in the category of artificial magnet. So there will be a magnetic compass will be like this. So you can say it is the dark one is a north pole, the other side will be a south pole, right? So magnetic compasses also comes under an artificial magnet. So these are the categories of the magnet, natural and artificial. Clear? The topic of today's is bar magnet, and most of the time we'll be discussing today about a bar magnet and its properties, right? So what is the topic now is bar magnet and its properties. Ready? Let me write. This is the bar magnet here. Properties one by one we'll be discussing. From the basic classes onwards, you might be learning the same, but still, let's consider this is an introduction class. So first property, attractive property. Let me write everything. So then one by one we'll be discussing. Bar magnet will have attractive property. And the same bar magnet will also have a directive property, and your same bar magnet will have a dipole nature. All right, dipole nature and law of poles, dipoles. We'll discuss about that. And this bar magnet repulsion is the sure test whether the magnet will have a dipole and the pole strength or not. You will understand repulsion is the sure test. See, I hope you remember in electrostatics, you might have learned during the properties of an electric dipole, right? So repulsion is the sure test of electrification. Whether the charging is done or not, you will be knowing only through the repulsion test only. With the property of attraction, you cannot find whether the given body is charged or not. So that may be through different phenomena, maybe through conduction or induction or any other phenomena, right? Clear? Or friction. Now, one more. Let's see, one more. One more will be the magnetic axis and a magnetic meridian. Magnetic axis and magnetic meridian. And you can write one more strength like pole strength, and the other one is a magnetic dipole, right? And magnetic dipole moment, right? So like this, actually speaking, there will be 52 properties, small or big or major concepts together. There will be 52 properties for the bar magnet, right? So what maximum we can discuss, we'll do it now. Listen, attractive property. What is this attractive property first? A bar magnet will attract another bar magnet or another magnetic substances. You know the magnetic substances. Here it is there. That's called attractive property. Magnet means the first thing will come into your mind is that attractive property. Simple. Directive property. For example, this is a bar magnet I have. If I hang this bar magnet, it will not align exactly like this. If you want, you can check. If you hang this bar magnet freely, it will align either in this way or in this way or in this way or in this way. That's it. Look at here. This is what the alignment. Never be like this. Never be flat. It will align in this direction, for example. Right? So this is the direction, is the indication of magnetic north pole or south pole, or geographic north pole or south pole. Remember, the more deeper analysis about Earth's magnetism will be discussing in the next session. So what is the topic? Earth's magnetism. The very interesting topic will be discussed in the next sessions. Then you will understand when you freely hang the magnet, in which direction it will come and align. That direction will be based on Earth's magnetism. Clear? Now, that's a directive property. What is the directive property? When you hang a magnet, a bar magnet freely, it will not align in the flat direction, it will align at some angle like this, right? So that's called a directive property. And what is this dipole nature and laws of dipole? Dipole means two poles. Monopole for a magnet will never exist. Is it clear? Monopole for a magnet will never exist. So look at here, there is a magnet. For example, a bar magnet we have. North pole and south pole is there. That means dipole nature is here. And what are the laws of poles? North pole and north pole repel each other. South repel each other, but south and north attracts each other. Same thing like charges. Like charges repel each other, like poles repel each other. Unlike charges attract each other, unlike poles attracts each other. Similar way. Clear? So that's what a dipole nature. And one important thing you should understand is, for example, I have this magnet which is cut into the two pieces. The two pieces I just wanted to show here. So this is one piece and this is the another piece. One piece, the other side south is existed already. This side is north existed already. Automatically, due to the phenomenon called induction. What is it called? Induction. So there will be north pole will develop here, there will be south pole will be developed here. You can check carefully. See here, there is a dipole nature automatically exists. So here also dipoles automatically exist. For example, further continues, if you cut this magnet also into another two, there also each part there will be a north and south exist automatically. That's called the dipole nature of a bar magnet, right? Which is also the law of poles, like poles and unlike poles, right? You know what happens. Clear? Now, repulsion is the sure test of magnetism. Repulsion is the sure test of magnetism. For example, I have a bar magnet. Let's come here. I have a bar magnet of north pole and south pole. And there is a magnetic substance is available here. It may be an iron piece is available here. When I brought this bar magnet close to the iron piece, definitely 101% this iron piece will be attracted by this magnet. How it is possible? Because of the phenomenon called induction. What happens? So there is a south pole is here, right? On this iron piece, so north pole will induce as long as this bar magnet is close to this iron piece. So the south pole is here, opposite pole will be induced here. When you take this bar magnet to the far distance, so this north pole will not induce. Okay, it will be just an iron piece. When I bring this bar magnet close to this iron piece, opposite pole will be induced here. So that will be the reason for attraction between this magnet and the iron piece. That's called repulsion is the sure test of magnetism. Finished. Right? Next. What is this magnetic axis and magnetic meridian? Magnetic axis and magnetic meridian. Look at the interesting thing here. I have a bar magnet here. This is the bar magnet of south pole and north pole. If you draw an imaginary line passing through the south pole and north pole, that's called the magnetic axis. So simple. The imaginary line drawn, imaginary straight line drawn from south pole to the north pole, that's called the magnetic axis. Right? Look at this interesting part. Imagine this cap, it's a north pole representation, and the back side, it's south pole. Right? So imagine a line drawn from south pole to north pole or north pole to south pole. That line is called magnetic axis. The axis must join both north and south poles. And you can assume or imagine a vertical plane passing through the north pole and south pole. Okay, a vertical plane passing through north pole and south pole. That vertical plane passing through north pole and south pole is called vertical plane. I am talking about. It will be the horizontal plane with respect to me. Clear? It will be an horizontal plane which is passing through north and south poles. Right. I am talking about a vertical plane passing through north and south poles. It's called a magnetic meridian. What is it called? A magnetic meridian. Understand? The vertical pole, what vertical plane passing north and south poles. Magnetic meridian. The most important property here, I had not mentioned, here I will write here, that's called a magnetic length. What is it called? Magnetic length. Here we should understand so much things, and we'll spend little more time on magnetic length now, because that will be the basic for the magnetic pole strength, magnetic dipole and dipole moment. Clear? Magnetic pole strength, dipole and dipole moment, and this will be the basic magnetic length. Clear? Now, what is the magnetic length here? There is a concept of displacement in physics, you know. In the plus one kinematics topic, you will get it. It's similar to the displacement. The shortest path between north pole and south pole, it's called the magnetic length. What is that? The shortest path between north pole and south pole. Imagine it's the south pole and north pole. South pole will not be located at the end of the magnet. At the same time, north pole also will not be located at the ends of the magnet. So they'll not be exactly at the ends, and they'll be somewhere here. Carefully. So they'll be somewhere here. Understand? Clear? And a shortest line between north pole and south pole, that's called the magnetic length. And this magnetic length, I'm writing here, this magnetic length is denoted with the symbol 2L. What is that? 2L. Exactly half of the length will be L, and the other half will also be L. It's 2L. And remember, this magnetic length is a vector quantity. Magnetic length is a vector quantity. It's a length. SI unit is meter, and it's a vector quantity. Vector quantity means it will have a direction, right? the direction of this magnetic length always from south pole to north pole. Remember, the direction of the magnetic length always will be from south pole to north pole. Remember, south pole to north pole. And there is a difference between the magnetic length and geometric length. That's a very important. This is called the geometric length from here to here. See here. This is called geometric length, and this is called magnetic length. I hope you understand. Which is more? Geometric length means the actual length of the magnet. If you consider the bar magnet is a simple iron bar or a steel bar, its length is called geometric length, and the shortest distance between the north pole and south pole, it's called magnetic length. And always the magnetic length will be lesser than the geometric length. Okay, magnetic length will be lesser than the geometric length. Is it clear? And there is a relation according to the physics and the chapter called magnetism and matter. There is a relation between them. So you know the relation between them will be magnetic length is equal to 5 by 6 times of geometric length. Magnetic length will be how much? Approximately 5 by 6 times of the geometric length. Understand? Clear? So this is about magnetic length. Magnetic length is a vector quantity. SI unit is meter, and magnetic length will be 2L, and magnetic length mostly in a vector form it will be written 2L bar. Okay, in vector form it will be written 2L bar. Okay. Now we'll be focusing more on magnetic pole strength, dipole and dipole movement, and some applications also we'll be discussing on pole strength and the dipole moment now. What we have discussed about magnetic length and geometric length. Let's see here. What was the relation? The magnetic length is equal to a 5 by 6 times of geometric length. Okay, here. Let me take two cases. The first case will be like this. There is a south pole and north pole. The geometric length is given as capital L. So I am writing the geometric length is how much? L. So what is the magnetic length? So your magnetic length is 2L. Clear? So if it is south and north pole, so this will be 2L. For example, if you take a half circular ring, it's like semicircular magnet I have. Semicircular magnet. The radius of this semicircle is R. Now the question, imagine it's a south pole here and north pole here. The question is, what is the geometric length and the magnetic length? So here the geometric length will be how much? From here to here. From here to here. The complete from here to. That's called the geometric length. What's the geometric length? It's half of the circumference of the circle, right? It's pi r. What is the magnetic length here? That's important thing. Magnetic length. The magnetic length is, what is the magnetic length? Magnetic length is the shortest distance between south pole and the north pole. Look at here. Is it the diameter of the circle? Definitely it's the diameter of the circle. It's 2r. Clear? So like this, your confidence and the concepts will develop. Now, let's understand the pole strength. What is the concept now? It's pole strength. Pole strength is denoted with the symbol M. What is this pole strength? If you consider a bar magnet of south pole and north pole, this pole will have a property of attracting or repulsing another magnet or a magnetic substance. So many times we discussed today itself. The ability of this pole, a particular pole, to attract or repel a magnet or magnetic substances is called pole strength. What is that? The ability of a pole in attracting or repulsing a magnet or a magnetic substance. So that's called the pole strength. And this is the pole strength is a scalar quantity. What is that? A scalar quantity. You know this SI unit of this pole strength, it's a very important. One of the APMT exams, this question was asked. SI unit of pole strength. Pole strength SI unit is ampere meter. What is that? Ampere meter. Pole strength SI unit is what? Ampere meter. Is it clear? Pole strength SI unit is ampere meter. Now, and one more important thing. And south to pole, see, pole strength is denoted with the symbol small m, right? South to pole is denoted with the pole strength minus m, and north to pole is denoted with the pole strength plus m. Minus m plus m. This is about pole strength. If this small m value is more, and you can say that that particular pole will have the more ability in attracting or repulsing a magnet or a magnetic substance. Is it clear? This is about the pole strength. That's simple things about the pole strength. Now, let's see the small application. Like this, so many applications we'll be discussing in the later classes. Simple, small application. How generally the concepts will be as it's minus m and it's plus m. Means it's south pole and this is north pole. I'm just cutting this magnet into two halves, horizontal halves. Concentrate on this magnetic pole strength. What happens? That also became half. Yes or no? So the new pole strength I am writing like m dash. M dash will become half of the initial pole strength, irrespective of the sign. Okay. Here also it will become half, and here also it will become half. And what about the magnetic length? So magnetic length, initially it's 2L, now it is 2L dash. Final, after cutting the given bar magnet, the final magnetic length is 2L dash, so it is not changed. You can find 2L bar and 2L bar. If you take this consideration of two individual magnets, the shortest distance between south pole and north pole, in the first case it's 2L bar, and second case also it's 2L bar. Clear? Seeing another application, let's see. This is minus m and it is plus m. Here I've cut the magnet into two halves in this way. Immediately you should understand the final magnetic length will become 2L by 2. Clear? 2L dash will be 2L by 2 because magnetic length became half in this magnet and in this magnet. And what happened to the pole strength? The final pole strength will remain same. Because poles we are not cutting into the halves. Okay. So this is about the simple application. Here you should understand the pole strength is depending on three important physical quantities, parameters or properties. The pole strength is depending on nature of the material. This is also one of the important questions. See, most of the chapter will be theoretical. Be prepared for that. Nowadays, a number of theoretical questions are also increasing in NEET exams. That's the reason we will be focusing each and every line. Right? Why to avoid? The pole strength is depending on the nature of material, and the same pole strength of a magnet also depending on area of cross section, Alright, if the area of cross section of that particular pole is more, and the pole strength also will be more. And extend up to what? The level of magnetization. Level of what? Magnetization. See, by using a phenomenon called friction, conduction and induction, we charge the body, right? Up to what level we can charge the body, it's there, right? It's according to our requirement. In the same way, according to the there are some methods of magnetizing a material. Okay, so that we'll be discussing later. Up to what level, what extent you can magnetize the material, so your pole strength depends on that part even. Okay, so pole strength of a magnet, this is the pole strength, no confusion at all. Small m is the pole strength, and this pole strength is depending on nature of the material, area of cross section, and extension up to what level of magnetization you have done. And the pole strength is independent of shape of magnet. That's the most important, right? So your pole strength is independent of the shape of the magnet. Is it clear? Everyone, I hope everybody is understanding the chapter. Now, the last topic for this session will be dipole moment or magnetic moment or magnetic dipole moment. No confusion at all, and it is denoted with the symbol m bar. Initially, it's clearly mentioned that it's a vector quantity. You know the electric dipole. Same way, it's a magnetic dipole. It's a vector quantity. And this magnetic dipole will be equal to, it's a product of the pole strength into magnetic length. Understand? It's a product of pole strength and magnetic length. So pole strength is a scalar quantity. Understand? So but magnetic length is a vector quantity. That's the reason this is also a vector quantity. Right? So the SI unit of this will be what? What is the SI unit of your pole strength? Here itself I have written. Pole strength SI unit is what? Ampere meter, right? So this is ampere meter, and this is also meter, length. So meter square. Ampere meter square is the SI unit of a magnetic moment or magnetic dipole moment or a dipole moment of a magnet, right? So remember this. And magnetic moment is a vector quantity. Vector quantity will have direction. I'm asking you once again, what is the direction of magnetic length from south pole to north pole, right? And in this magnetic moment is also there is a magnetic length. So that means, so this magnetic moment also will be directed from south pole to the north pole. That's it. I hope the new chapter will be interesting for you. It will be more and more interesting in further sessions. Thank you very much. All the very best.